Okay, let's continue. In the last class, we essentially saw that all your single stage OTAs you can approximate as a first order system, and then we saw if you take such a first order system and put it in negative feedback, will it become unstable or it will be stable? A first order system, if I put it in negative feedback, we saw that it was guaranteed to be stable, right? And then we also saw that for a first order system, the unity loop gain frequency exactly equals the closed loop 3 dB bandwidth, which is in turn the feedback factor times the DC gain times the pole location. So although a first order system or single stage OTAs being a first order system is nice with respect to stability, what was one issue with single stage OTAs? What was a drawback with single stage OTAs? We can't drive resistive loads, so that made us go for a multi-stage OTA structure. But the moment we have multiple stages in cascade, the overall system is no longer a first order system, so we do not know if it is stable or not. So we'll have to see what do we do for making it stable. So that's where we are right now. So let's continue. So again, to recap, the closed loop transfer function is the open loop gain A of s by 1 plus beta times A of s, where here the loop gain is what we defined as beta times A of s. And strictly speaking, here by the way, A of s is your transfer function of the multi-stage OTA, which is a higher order transfer function, right? And strictly speaking, if you were to see if the closed loop system is stable or not, you'll have to look at the poles of this closed loop transfer function and see if it is in the left half of S plane or not. Now, for a first order system, it was trivial to calculate the closed loop pole, but if you have a higher order system, finding this polynomial, finding its roots, it's not trivial. So that is why we try to see if we can make sense of the closed loop stability only by looking at the loop gain, right? And if I give you a loop gain transfer function, what might be a metric that you might use to see if it is stable or not? You have to see if the closed loop poles are in the left half of S plane or not. But what I'm saying is you can't compute the closed loop poles all the time. So you typically try to see if you can make sense of the closed loop stability only from the loop gain. Now, if you are given a loop gain transfer function, what might be a metric you might use to quantify the closed loop stability? But that's not, it's a tool, but what might be a metric or parameter that you might use? Okay, so if it's not clear, let's do it. So what are the techniques you know for finding closed loop stability? Okay, Nyquist plot, and then so root locus. You guys told root locus also. And what is the simplest you can do for? What is the simplest tool you know? Bode plot, right? That's the simplest thing. Now, of course, usually these two guys give the complete information of the stability, Bode plot, but it's easier to sketch. So typically we try to understand the closed loop stability based on one of these, translate that understanding to Bode plot so that we don't have to sketch Nyquist or root locus plot every time. Only from the Bode plot we do it. And although typically it is done through Nyquist plot, I will take an alternate approach and look at root locus, because if I have to explain Nyquist plot, I have to explain you complex analysis, Riemann zeta function, encirclement this side, that side, Cauchy's integral, blah blah blah. So we just look at root locus. As we'll see, this is very intuitive and more logical to plot. Okay. So we'll quickly look at root locus. And again, I just want to mention that the point of this lecture or this course is not to make you comfortable in plotting root locus. At the end of it, if you're not comfortable in plotting root locus, it's completely fine. That's not the focus. The focus is to use root locus as a tool to make some comments about the closed loop stability. That's it. The key takeaways must be those comments. That's it. Okay. Even if you're not able to completely take notes, it's fine. Just try to follow with me and we'll just take away those final key points. Yeah, and root locus, as you know, plots the roots of this closed loop transfer function, which is 1 plus beta A of s. So this is finding the roots of 1 plus beta A of s to be 0. And I'll write A of s as beta times A naught times a numerator polynomial by denominator polynomial. And this in turn I can simplify it like this: d of s by d of s plus beta times a naught n of s. So like root locus plots the closed loop poles with respect to what? With respect to? Huh? No, I mean, see, this has nothing to do with frequency. It's a math function. You have a polynomial. You're trying to sketch how the roots of this polynomial varies as you vary one of the parameters in this, and that typically is the d secant a naught. This is a simple math problem you might have learnt in your JEE preparation or something, right? Locus of an equation. That's it. So that's what we try to do, and again I'll just make a couple of points on how this root locus plot might look like. That's it. See, let us say you start with a naught to 0. If I make a naught to be 0, the polynomial reduces to d of s equal to 0. What are the roots of d of s equal to 0? Huh? Poles of what? Poles of what? No, poles of closed loop is the roots of this fellow. If I just take the roots of d of s equal to 0, what will that give me? Poles of the open loop transfer function, right? So that is something, it's trivial. Closed loop poles, it starts at open loop poles. Similarly, if I make a naught infinity, here only this term will dominate, correct? So which means n of s equal to 0 is the effective polynomial. If I find the roots of this fellow, what will that give me? Open loop zeros. This is open loop zeros. So this is one thing we obviously know. If I change the d secant from 0 to infinity, the root locus start from open loop poles and end at open loop zeros. This is one observation we'll make, and I'll just make one more observation and then we are good enough to start plotting. See, I am trying to plot the closed loop poles, and the closed loop poles, remember, they are complex numbers, so which means we try to plot it in the complex S plane like this, sigma j omega. So again, the closed loop poles can be a real number or a complex number. Let's try to see when can it be a real number. The equation we are looking at is this: beta a naught 1 plus beta times a naught times the numerator by denominator, that I will call it as some function f of s to be 0. Now let us say the closed loop poles, one of the closed loop poles is purely real. So let us say I say that s equal to minus sigma k is a pole. So which means this should satisfy this equation: 1 plus beta a naught f of minus sigma k must be 0. Fine. So which means, what can you say about f of minus sigma k? Will it be greater than 0 or it will be less than 0? Yeah, why? This is equal to 0, but from here how can you conclude this should be less than 0? Correct. Yeah, so this essentially means this has to be minus 1. So beta a naught is positive, so this has to be negative, right? Even if f of minus sigma k is minus 0.1 or something, as if you can use an appropriate value of a naught to satisfy this equation and make the value 1. But this has to be satisfied that this polynomial must evaluate to be a negative number. If this is negative, I can choose any value of a naught and make it minus 1, right? Okay, and let us say now my polynomial f of s is looking like this. Say it has a lot of poles, s plus p1, s plus p2. Let us say there are n poles like this. Now we are trying to substitute minus sigma k here. So there will be n terms here. So let us say there are n products you will have. N terms are there, right? Now you have product of n terms, and this product must be less than 0. If product of n terms has to be less than 0, how many of those terms has to be less than 0? Odd number of terms has to be less than 0, so that effective product is less than 0. So here I am putting, let us say, minus sigma k. If the first term has to be less than 0, what can you comment about p1? P1 should be smaller than sigma k or larger than sigma k? If this has to be less than 0, what can you say about p1 and sigma k? P1 must be less than sigma k. Fine. So that's the other translation. If you need to have a real pole, you know that odd number of terms has to be less than 0, which means odd number of poles has to be less than sigma k. Fine. So which means, for example, if I have 3 poles like this, open loop poles, if let us say one of the points on the real axis must be a closed loop pole, I should have odd number of poles. You can extend to zeros. Odd number of poles and zeros must be to its right. This is fine. So any point here can be a closed loop pole. This I'm sure you would have seen. So I'll just mark it here. So on the real axis, I'll say odd number of poles and zeros to the right. Fine. So I mean, we'll just use these two observations, simple observations, that root locus starts from open loop poles, terminate at open loop zeros, and if the root locus has to lie on real axis, the number of poles and zeros to the right must be odd, right? Only then the product will be less than 0. Is this okay? Cool. So now let's look at some simple examples so that we get used to this. So I'll take a first order system like this. I just have one pole. So again, root locus starts from this open loop pole, should terminate at open loop 0. Where is the 0 here theoretically? Infinity. So it should start from here and go to infinity. Can go to infinity along the real axis or in the complex S-plane. So let's see if we can have something on the real axis. Can I have anything on the real axis? If I need to have something on the real axis, I should have how many poles and zeros to the right? Odd. So here how many poles I have to the right? One is odd or even. So I can have something here. So which means the closed loop pole will start from here and then will branch out to infinity as you keep increasing the DC gain. Fine. So again, this proves that a first order system, if you put it in negative feedback, it is guaranteed to be stable because the closed loop pole is definitely on the left half of S-plane. Right? So let's look at second case. So let us say now I have a second order system. So again, I have 2 poles. Again, root locus starts from these 2 points. Now should go to infinity. Again, infinity means it can be on the real axis or in the S-plane. Let's look at if it can go on the real axis. So can I have a portion of the root locus here? No, I have even number of poles. Here I can have it there. So which means that this will be a part of the root locus. So that means one pole does this, other pole does this. Now this has to go to infinity. Looks like I cannot go along the real axis. So obviously it has to branch out to the complex S-plane. So I have 360 degrees. I have 2 poles. What will happen? I mean 360 degrees will be divided by 2. One will take one half, other will take the other half. Without going to too many details, this seems the logical thing that will happen, and that's what actually happens also. So as you increase the DC gain A0, the poles start from here and kind of branch out to the S-plane. So now tell me if a second order system can become unstable. Yes or no? If yes, why? If not, why not? Yeah, why can't it become unstable? Yeah, again, you see the closed loop poles definitely lie on the left half of S-plane. So this is not going to be unstable. Right? But the problem is the following. For a large DC gain, you see that the closed loop poles kind of branch out to the complex plane. So which means you will have a pole like this, minus sigma naught plus or minus j omega naught. Right? So if I have a pole of this form, if I apply a step to the system, how will the step response look like? Exponentially decaying. But I have an imaginary part plus or minus j omega naught, right? What will happen? Huh? Yeah, it will be a decaying oscillations like this, right? So it will look like this. Whereas, I mean, where the sinusoidal part will correspond to the sinusoidal frequency will correspond to omega naught, and this exponential decay will correspond to e power minus sigma naught t. Is that fine? I mean, remember, if I have a pole P1, the response will be of the form e power P1 times t. That's it. correct? This is the eigenfunction. Okay, anyways, let's move on. But this is not something you want, because if I apply a step, I want my output to nicely settle like this smoothly. So which means if I should not have any kind of ringing like this, can you tell me where should the closed loop poles lie then? It should lie on, yeah, negative real axis, correct? If it branches out to the complex plane, we definitely have this sinusoidal ringing. So if you do not want any kind of ringing, the closed loop poles must lie on the real axis. I will mark it here, should lie on real axis to avoid any kind of ringing. Is this clear? So this is one takeaway we will have, that we want to make sure that our closed loop poles will should lie on the real axis to have a good settling. Okay. So then we have been looking only at poles. Now let's look at zeros, because zeros will feel left out. Now let's see. Yeah. So now I have taken a second order system again here. I have two poles, but I have introduced one zero. So this way we can see how will the what will be the effect of the zero also. Right? So again the same thing. It will start from the open loop poles and should go at open loop zeros. So one of the zeros is here. So one of the poles should terminate here. Other pole should terminate at infinity. Again, let's look at the portion on the real axis. So can I have something here? I have odd number of poles and zeros. So I will have something here, and then I can have only something here. Fine. Now, one way to think of how this root locus will vary is the following. Assume that the zero is not there, or zero is at like infinitely large frequencies. If the zero was not there, we knew that the root locus was doing something like this, correct? But now I have a zero, which means it cannot go to complex S-plane forever. So one of the poles has to terminate here, other pole has to go to infinity along this line. So what is the logical thing that should happen? It is starting out this way, but it cannot go on to this complex S-plane forever. It cannot get lost in the plane. One has to come down and terminate here, other has to go to infinity here. So what is the logical thing? Basically has to do some kind of transition to the real axis here. So it does this, and then one of them will terminate at the 0 here, other will terminate to the 0 to infinity. Again, we don't have to worry about what this point is, and so on. We just want to get a qualitative sketch of what happens to the poles. That's it. So now tell me, if when I introduce this left half plane 0, do you think we are doing better with respect to stability or not? Yeah, why? More left half plane is okay. Here also, that's more important, right? We wanted the closed loop poles to lie on real axis, correct? When I didn't have any zero, this was not carrying anything. It was just going to infinity without doing anything. But the moment I have a zero, the zero is acting like some kind of a magnet. It is not allowing the poles to branch out to infinity along the S-plane forever. It is making it fall back on the real axis, making the system more stable. Is okay? So this is another takeaway we can have. Left half plane 0, I will say, is good for stability. Cool. So now let's take a third order case. So here I have 3 poles. So again, the root locus will start from these poles and go to infinity. Let's look at what portion can lie on real axis. This portion will be on real axis, and this portion. That's it. Right? Now again, I have 3 poles. They have to go to infinity. I have 360 degrees of S-plane. So I have 3 of them. How will it get split? 360 by 3, 120, 120, 120. I mean, simple land division problem. We have a land divided amongst 3 siblings. To be fair, you share it equally. So one of them will take this, other will take this, other will take this. So you have 120, 120 and 120. Again, I'm not going to a lot of details on what point it branches out and stuff, but seems like this is the logical thing that will happen, right? So now tell me if a third order system can be stable or it might become unstable. Yeah. You see that after a particular DC gain, let us say I call this A0 prime. If I keep increasing the DC gain, the moment I have a DC gain greater than A0 prime, the closed loop poles enter the right half of S plane, it becomes unstable. So I will say if the DC gain is greater than A0 prime, this becomes unstable. And I will give it as an exercise to work out, and you will find that this gain, I mean, if the gain was, let's say, million or something, it is okay, right? I can at least have a gain till million and make sure things are stable. But as we'll see, this gain is pretty small. This is kind of useless if you have such a small DC gain. Okay, so now let me do one last case and then we'll wrap up root locus. So let me copy this here. So here I have taken a case where I have the same 3 poles, but I've introduced 2 additional zeros here. So again, let's quickly see. So as usual, they have to start from these 3 open loop poles. 2 of them have to terminate here. One of them has to go to infinity, right? So let's quickly look at the real axis part. So here I have something. Here I'll have something. Here I'll have something. That much is clear. Again, the way to visualize this is as follows. Let us say there are no zeros. Then we know for a fact that the poles would have done something like this, right? But now the zeros are present, which means they cannot do this forever. One of them has to terminate here, and that is already happening here, correct? One of them has to end here, other should go to infinity, right? So which means the logical thing is it might do this. Now again, depending on whether, depending on how far or how close the poles zeros are, this might not even enter the right half plane. It might just do this also if the zeros are close by. If the zeros are far apart, it might be in the RSP for a longer time and then it will do this. But for now, we'll take a case where it enters the RSP for a small values of. So once again, you see that the LHP 0 is actually helping you. Right? So it is kind of acting like a magnet and attracting the poles to fall back. And the lame analogy I give is poles are like naughty children at home. If you have so many naughty kids at home, they kind of become unstable, break things at home. But the moment you have 2 strict parents at home, they'll make sure that they cannot kind of go naughty and unstable. They'll make sure that the kids fall back in line and things become stable. So we'll just take this root locus plot and let's try to translate this understanding to a Bode plot. Okay. So let me copy this, and I already have the Bode plot plotted here. So I'll just show that. Yeah. Let me. So here I am showing the Bode plot. So again, I have 3 poles. This is the first pole, second pole, third pole. And after 3 poles, what will be the slope here? Minus 60 dB per decade. Assume this is minus 60 dB per decade, and then I have 2 zeros. So the slope becomes minus 40 and minus 20. Here I am showing the face. The face I have not drawn exactly to scale. It might not match the pole locations, but it is a very rough plot. If I have just one pole, face will start from what value and end with what value? 0 to minus 90. I have 3 poles, so the phase should go to what value? Minus 270. It seems to go to minus 270. But then I have 2 zeros. If I have one left half plane 0, the phase will increase or reduce? Increase by what value? Plus 90. So I have two zeros. It should increase by 180. So it goes to minus 270 and then increases by 180 degrees. So it reaches to minus 90. It's just a very rough plot. Okay. I mean, it's okay if you're not able to sketch it on your notes, it's fine. Just pay attention. Just the final takeaway is the main importance. Okay. Okay. So now let me actually try to bring your attention to this point on the root locus, where the DC gain is some A0 prime. Oops, sorry. For this value of DC gain A0 prime, can you make any comments about the closed loop poles? Huh? No, I mean, yeah, that is a jargon, but what can you say about the closed loop poles? They are lying on the imaginary axis, right? If for this value of DC gain, you see that closed loop poles lie on the imaginary axis. And remember, the closed loop poles are the roots of this equation, 1 plus loop gain equal to 0, correct? So which means if the closed loop poles lie on the imaginary axis, if I substitute S as j omega, for some value of omega naught, this will get satisfied, right? I mean, ideally this can be a complex number, but looks like for this value of DC gain, even if I make S to be a purely imaginary number, the equation will get satisfied. So which means, you guys know this already, this is minus 1. So what is the magnitude of the loop gain now? And what is the phase at that frequency? Minus 180. Okay. And what is special about this DC gain A0 prime? Why am I looking at this? Yeah, after the DC gain, the pole center RHP, right? So that's why this is the kind of limit for you. So let's try to sketch the corresponding Bode plot here for this DC gain A0 prime. Let's say this is some A0 hat, okay? The DC gain is some A0 hat here. Now I want to sketch the DC gain, sketch the Bode plot corresponding to this DC gain A0 prime. So if I change the DC gain here, what will happen to the magnitude plot? It will shift up or down. Remember, this is all in log scale. So again, this is 0 dB. This will just keep shifting up or down, correct? So, but what will happen to the phase? If I change this DC gain A0, what will happen to the phase? Phase will not change, so this is going to remain the same. So essentially I have to look at a point where the phase is minus 180. So let us say this point. At this point I should have a case where the magnitude is 1, right? So you can think of it like this. Let us say you start from very small values of DC gain. So which means the Bode plot might be here somewhere, okay? And then you keep increasing the DC gain so that for the DC gain A0 prime, when the phase is minus 180, the gain is exactly 1. 1 is 0 dB, right? So let me actually copy this. This also I have marked it. I don't want to draw it here. So I have already drawn it here. So as you see, this is the point. This is basically scaled down. Okay, so if I were to write it, this is beta some A0 hat, and this is beta A0 prime. Fine. Cool. So now let us say you keep increasing the DC gain here in the root locus. So the poles are in RHP, and what happens after if you keep increasing further? If I keep increasing beyond A0 prime, the poles are in the RHP, but if I keep increasing it further, what happens? They start to enter LHP. So this is the other boundary. Let us say A0 double prime. So at this frequency, what can you, at this DC gain A0 prime, what can you say about the closed loop poles? They are again lying on imaginary axis, right? So which means if we try to sketch that here, so I'm essentially increasing the DC gain. So I keep increasing it, and remember the phase is becoming minus 180 here again. So after some point, this will happen, right? So again I have sketched that also here. So let me actually So these are the points. So let us say this is beta a naught hat, this is beta a naught double prime, this is beta a naught. So a naught prime is this one, a naught double prime corresponds to this one, right? This is all in dB. Okay. And what can you say if, let us say, the DC gain is between okay, let me mark that here, this is a naught double prime. If the DC gain is between a naught prime and a naught double prime, from the root locus, what can you say about the closed loop system? It is unstable. That much is clear. So let's try to translate that here. So this is the Bode plot, magnitude plot corresponding to the gain a naught prime. This is the plot corresponding to a naught double prime. So which means any magnitude plot in this region will correspond to an unstable system in closed loop. Fine. So this is the region where you have unstable magnitude plot. This is fine. So now let's try to get a better understanding. So first of all, how did I conclude that this is the magnitude plot corresponding to a naught prime? I mean, how did I say that? How did I plot this Bode plot and say that this is the magnitude corresponding to a naught prime? Yeah, at this I mean, for this value of DC gain a naught prime, when the phase is minus 180, the magnitude is 1, right? This is the point. Same for a naught double prime, right? So this is your boundary, and any magnitude plot here will correspond to an unstable closed loop system. Okay. So let us say now I take some example system. So let us say I take some system here, some magnitude plot here. This is definitely unstable. So now if I check the phase where the magnitude is 1, what can you say about the phase? Yeah, absolute value of the phase is greater than 180. And for that matter, any magnitude plot you take here, whenever it crosses 0 dB line, which is unity, if you look at the corresponding phase, the absolute value will be definitely greater than 180. So that's the mapping from root locus to Bode plot. So the idea is this: you look at the phase where the magnitude becomes unity, right? And what frequency is this? I mean, what is the name we gave for this frequency? The unity loop gain frequency. So I look at the phase of the loop gain where the magnitude becomes unity. Correct? If the, let us say, to avoid the confusion on negative positive, if I take the absolute value of this phase, if this is greater than 180, which means that the system is definitely unstable. That is the final translation from root locus to Bode plot. Okay. So now let's take this case. This magnitude corresponds to some DC gain a naught hat, and let us say that crosses unity at this frequency. At this frequency, I look at the phase, and the phase, as you see, the absolute value of the phase is definitely less than 180. So this is definitely stable. Now, of course, it is not just enough to say if the system is stable or not. You want to quantify how stable or how close to instability it is. So you see how far away this phase is from 180. And what is this called? Phase margin, right? We'll call it PM or whatever. So which means if the system must be stable, the phase margin must be greater than 0 or less than 0? Must be greater than 0. I mean, this is the margin you have, that is the excess phase you can have in your system, that make sure that the phase just reaches minus 180, right? So that's the final understanding. You should have a case where, I mean, let me rewrite it here. If I look at the phase of the loop gain at the unity loop gain frequency, and to avoid the confusion on negative, I will just take the absolute value. If this is less than 180, or I will say other way, if this is greater than 180, this means that the closed loop system will be unstable. And to quantify how close to instability the closed loop system is, we define the phase margin, that is 180 minus this phase. That's it. Again, I am just taking the absolute values to avoid confusions on negative signs. Okay. Is this clear? This is the final check you have to do. So now let me ask you this question. I'm sure you have seen this before, right? This is not the first time you are hearing, I believe. I'm just doing it again. So let me ask you this question. So let us say I give you a loop gain. Okay. And let us say at some frequency, say omega x, I look at the phase of the loop gain, and that is minus 180. Plus 180 minus 180, I mean same, okay. And at that same frequency, I check the magnitude. That is let us say 20. Now can you say if the closed loop system is stable or is it unstable? How many of you are for unstable? I mean, there are two options, stable or unstable, right? I mean, what do you want to vote for? Unstable. No one wants to make the system stable. What is marginally stable? Now we have third option. Okay, I mean, which means you have to relook at the understanding once again. See, what is this check we have to do if the system is stable or not? Phase margin. Or we just look at the phase at the unity loop gain frequency, right? That has to be less than 180 degrees. So what is the information given to me right now? Maybe if I sketch it again, let us say this is the magnitude here, and here I sketch the phase. What is the information given to me? At some frequency omega x, the phase is minus 180. So let's say this is minus 180. At some frequency omega x, the phase is minus 180. But what is the magnitude at that frequency? 20. So let us say this is the magnitude, this is 20. But what is the check I have to do for checking if the closed loop system is stable? Yeah, I should check the phase when the gain is 1. Right? See, I just know that, I mean, one thing is for sure, let us say the gain is dropping at high frequencies. So I should check the phase at this point. I just know the phase at this frequency. Can you make any comments about the phase at this frequency? Yeah, it can go up or it can go down. If you have a left of plane 0, I mean, here that's what we saw, right? The phase was actually going up because we had the left of plane zeros. So here you can have two possibilities. It can actually go up and nicely become stable, or it can also go down, right? So what should be the correct answer now? Yeah, you cannot say. Third option, this is like the quantum realm. You say it's not possible. It can be both stable and unstable. Until I open the box, I don't know if the cat is alive or not. Similarly, until I know more information about the system, I cannot say if it's stable or not. Right? And if the phase has to continuously reduce like this, can you tell me if the system can have left of plane zeros? If the phase has to continuously reduce, do you think the system can have left of plane zeros? It cannot have. So if I give you an additional condition that, let us say it is an all pole system, then you can, this is the third information given to you, then you can conclude that this is unstable. Okay. Otherwise you cannot make any comments. This is a common misconception that, if the gain is 180 but the phase is, if the phase is 180 and the gain is greater than 1, it is unstable. It can actually become nicely stable. In fact, we will see a lot of systems we use will have this condition actually. So the ultimate check is the following. See, the final check is this: always check the closed loop poles if it is on the RHP or LHP, right? But that understanding maps to this statement that you only look at the phase at the unity loop gain frequency. That has to be less than 180 degrees for the system to be stable. That's the only condition. You cannot say if the gain is greater than 1 at the phase at the frequency where the phase is minus 180. Cool. So now at least it is the phase margin that we have to check. Now let us say I tell you that the phase margin is less than 0, then the system is stable or unstable? It's unstable. If it is unstable, where do you think the closed loop poles will lie? Lie on right half of S plane, so somewhere it might, right? If the phase margin is 0, where do you think the closed loop poles might lie? Where? Exactly on the imaginary axis. Now if phase margin is greater than 0, but let us say that it is some 4 or 5 degrees, where will the closed loop poles lie? It will be in the left half of S plane, but it might be very close to the j omega axis. So again, it is not just enough to have a positive phase margin. You need to have sufficiently large phase margin so that it is not close to the j omega axis. And how close or how far apart this must be depends on multiple parameters. One parameter is the following. See, let me take this second order example. Let me take a second order system. Let us say it has 2 poles. Now if I sketch the root locus, I know it does something like this, right? Okay. Now ideally, to have a good settling, where do I want the closed loop poles to lie? On the real axis. That much is clear. We already made this conclusion. Closed loop poles, you want them to lie on the real axis, because if it's on the imaginary or the complex plane, you will have sinusoidal ringing. So now we know that it has to be on the real axis. But do you think I can have it, let us say, far apart like this, or do you want them close enough like this? Maybe use different colors. I have 2 possibilities. One is to keep them far apart like this. Other option is to keep them close enough like this. Which do you think is a reasonable thing to do? Why? No. See, this is definitely stable. Second order system, right? Second order system is definitely stable. No confusion. Now, I want to understand where do you want the closed loop poles to be on. We are convinced, we are on the same page that the closed loop poles must be on the real axis. But on the real axis, I can choose multiple possibilities. I can choose them to lie somewhere here so that they are far apart, the closed loop poles. Or I can keep them close enough. Which is better? Why? Okay, you're saying other pole is on the j, but it's on the real axis, right? It doesn't matter. Sorry? Which one? Let me call it PA and PB. Which one do you think is significant? PA is insignificant. Sorry, hold on. Yeah, PA is insignificant, you are saying. Yeah, why do you want to do that? Okay, but let us say you want the system to settle really fast. Okay. Let us say apply some disturbance or some input. I want the output to settle really fast. What might be the optimal place to have the poles? Far apart? Okay, let's say it's far apart. So I have 2 poles, PA and PB. Which of them is the dominant pole? PB is the dominant pole. And why is it called dominant pole? It decides the settling, right? So right now this is the slowest pole, or the smallest pole. This is the slowest settling. So I want the system to settle fast. So what do you want? How do you want this dominant pole to be? Do you want it to be at a higher frequency or lower frequency? Let us say you keep increasing this, but if you keep increasing this, what happens to PA? That tries to come this way. So then what is the optimal point to keep? Keep them bang on the middle, right? Because if you keep increasing PB, you see that after some point this will become the dominant, non-dominant pole, TA will come here, and that will start to dictate your settling, right? So the optimal place is to make sure both of them are on top of each other. I mean, if you extend the analogy, I told if you dominant pole is like a slowest eater in a group of friends when you go for mess. So the optimal time for the group to leave is if everyone finishes eating at the same time, right? So if everyone is of the same speed, then no one has to wait for anyone else. That is the optimal case for speed. And what is this kind of settling called? A second order system. Closed loop poles are exactly equal. What is that condition called? Critically damped. At least looks like with respect to the fastest settling, this is the best condition to have, right? Is that clear? And I will give it as an exercise. You can work out and show that the phase margin for this case is 76 degrees. So this might be one phase margin to aim for. Okay. Now tell me, if I branch out to the complex S-plane like this, right? Let us say the closed loop poles are here in the complex S-plane. Do you think the phase margin is higher or smaller than 76? Yeah, why? If the closed loop poles are lying on the S-plane, do you think the step response is good or step response is bad? It rings more, so which means I can say that it is not really good. So which means the system is less stable compared to this condition. I mean, if I have more and more sinusoidal ringing, I know that it is not really very stable. So then can you comment about the phase margin here? Is it greater than 76 or less than 76? Right? So if you keep increasing this way, the phase margin reduces. And if I keep going this way, what can you say about the phase margin? That's the only possibility, phase margin increases. And that was the limiting case where one of you had mentioned. So if I push one of the poles to an infinitely large frequency, then you end up with a first order system, right? If I have first order system, what is the phase margin I can have? For a first order system, the maximum phase can drop is how much? Minus 90. One pole, so it goes to minus 90. So you have a margin of how much degrees? So first order system can have the maximum phase margin, and as you keep going this way, the phase margin increases. But that might not be the best case for settling. Best case settling happens when you have critically damped condition like this. Okay. So this is one condition to aim for, but you can also have another constraints imposed based on the closed loop response. So let us say the closed loop transfer function is 1 by beta times the loop gain by 1 plus loop gain. And let us say I have a first order system. What is the phase margin? 90 degrees. If the phase margin is 90 degrees, what can you say about the loop gain at the unity loop gain frequency? At the unity loop gain frequency, what can you say about the magnitude of the loop gain? Magnitude is 1. What about the phase? Phase is 90 degrees. Sorry, phase margin is 90 degrees. So what should be the phase? Minus 90. So how will you write the complex number as? Magnitude is 1, phase is minus 90. E power minus j pi by 2. And how much is this? How much is this? E power minus j pi by 2. Minus j. So now if I try to find the magnitude of the closed loop transfer function at the unity loop gain frequency, this is 1 by beta times minus j by 1 minus j. So how much is this? Yeah, 1 by root 2 times 1 by beta. Right? So again, this again proves that for a first order system, the unity loop gain frequency is equal to the 3 dB bandwidth, right? So if I sketch it quickly, so this is the unity loop gain frequency. If you have a phase margin of 90 degrees, you will have something like this. Okay. So let us say I have a phase margin of 45 degrees now. Then what can you say about the loop gain at unity loop gain frequency? What is the magnitude at the unity loop gain frequency? What is the phase? If the phase margin is 45 degrees, yeah, phase is minus 135, that is minus 3 pi by 4. Okay. Now if you substitute this value for loop gain and calculate the magnitude of the closed loop transfer function at the same frequency, can just work out, you will find that this is actually greater than 1 by beta. So you will have some kind of peaking like this. And let's say I take a limiting case where phase margin is 0 degrees. If phase margin is 0, what can you say about the loop gain? Magnitude is 1. What is the phase? Minus 180 e power minus j pi, which is what? If you put minus 1 in the denominator, what happens? So that's what will happen if you reduce phase margin. So this is the thing where phase margin keeps reducing, right? So this gives you another criteria. Ideally, you don't want any kind of picking in the closed loop transfer function. So again, I will give it as an exercise, simple calculation. You can work out what is the phase margin so that there is no picking in the closed loop transfer function. So you can find out what is the phase margin so that the closed loop transfer function at the unity loop gain frequency is exactly 1 by beta, and you will find that this is about 60 degrees. So again, you can use 60 degrees, 76 degrees as a good case, but if you are not able to meet that much also, at least 45 degrees is a typical number. So I'll stop here and we'll see.